and the topic of my presentation is basically what properties on fluids properties. See, properties of fluids. These are the topic. Basically, fluids. What is fluids and what is the introduction? We'll start one by one. This is the content, that is introduction, fluids, continuum, and fluid properties. Basically, we have different parts. That is, if we talk about the introduction. So first of all, we'll start from the introduction. Basically, fluid mechanics. What is fluid mechanics? Fluid mechanics is the science that deals with the action of forces on fluid at rest as well as in motion. In case of sub branches of fluid mechanics, we have fluid statics, fluid dynamics, and fluid kinematics also. So we will discuss one by one. What is fluid statics? Fluid statics is nothing but study of fluid at rest. And if we want to study the fluids in motion, and when pressure forces are not considered, then this type of a study is known as fluid kinematics. In case of fluid dynamics, the fluid in motion, but there is no consideration of pressure. There is a consideration of pressure forces. It means that if we are not considering the pressure forces while studying the fluid motion, then this type of study is known as a fluid kinematics. But if we want to study the motion, fluid motion, and pressure forces are considered, then this is called the fluid dynamics. So come to the next slide. Basically, in case of fluid, what is fluid? We'll discuss the fluid and its properties. Basically, fluid is any substance that can flow is called fluid, and fluid may be liquid or it may be gas. So these are the two forms of the fluids. Now, as we all know that matter exists in two states, that is solid state and fluid state. This classification of matter is based on the spacing between different molecules of the matter as well as the behavior of the matter when subjected to stresses. So here there are fluid exists in two forms. The first one is liquid and second one is gas. So we will discuss in details in terms of the fluid properties. So there are number of types of properties of fluid basis. First fluid property is mass density. Next is specific weight, specific volume, specific gravity, viscosity, surface tension, vapor pressure, capillarity, and cavitation. So there are a number of properties that is based on the fluid, which is called as fluid properties. We will study one by one. First of all, we'll discuss about the mass density. So what is mass density? Mass density is nothing but mass per unit volume is called the mass density. It is denoted by capital D, and mathematically we can define density is equal to mass upon volume. So m is mass here and v is the volume. Basically, SI unit of density, or you can say that mass density is kilogram per meter cube, and mass density of the water at 4 degrees centigrade is 1000 kilogram per meter cube, while 1.20 kilogram per meter cube for air at 20 degrees centigrade atmospheric pressure. So this is the mass density. So come to numerical based on the mass density. So we have a numerical based on the helium gas. The quantity of helium gas at 0 degree centigrade with a volume of 4 meter cube has a mass of 0.712 kilogram and standard atmospheric pressure. So we have to determine the density of the sample of the helium gas. So first of all, we will take what are the given parameters. So volume is given as 4 meter cube and mass is given as 0.712 kg. Density we have to find out. So density is equal to mass upon volume. Then m is mass and v is the volume. So we will put m as 0.712 and v volume as 4 meter cube. Then final the density of the fluid is 1.178 kilogram per meter cube. Now what is specific weight? Specific weight is another name that is weight density. It is denoted by gamma. So we have defined as what is specific weight. Specific weight is defined as the ratio of weight per unit volume of the fluid, and its unit is that is Newton per meter cube in SI, and the formula for specific weight is gamma equal to rho into g, where rho is the density of the fluid and g is the acceleration due to gravity. Now we'll talk about the specific volume. What is specific volume and how it occurred, and what is the mathematical relationship between the specific volume and density we have to know. So what is specific volume? Specific volume is nothing but only the volume per unit mass of the fluid, and the specific volume mathematically is defined as the volume of the fluid per unit mass of the fluid, and its formula comes down to 1 by rho. Rho is the density of the fluid, it also known as mass density. So we can say that specific volume is the reciprocal of mass density. Now we'll talk about the specific gravity. What is specific gravity and how it can take place, and how the numerical can be solved of the specific gravity base. So first of all, we have to need the basic definitions of the specific gravity. So we'll define the specific gravity. Basically, it is the ratio of specific weight of the given liquid to the specific weight of the water at 4 degree centigrade standard reference temperature. So it is denoted by capital S. Capital S is a specific gravity, and we have to know all that specific weight of water at atmospheric pressure is 9,810 Newton per meter cube. Basically, the specific gravity of the mercury at 20 degree centigrade is calculated as follows: S indicate for specific gravity and Hg for mercury. So, what is the value? That is 133 kilonewton per meter cube divided by 9.81. So, if we calculate the specific gravity of mercury, then it comes under 13.6. So, in some numericals, the specific gravity of the mercury is not known in the exam. So, we have to learn what is the value of specific gravity in case of mercury. So, it is of 13.6. Now, the next fluid properties is known as viscosity. So, we will understand the viscosity concept and how it can be calculated. We will understand the concept. Basically, viscosity is the resistance offered by one liquid layer over the another adjacent liquid layer. So, we have suppose we have fluid, and it always fluid flows in layers. This is the first layer of fluid, this is second layer, this is third layer, this is fourth layer, like that. The number of layers of fluids are moving, and fluid moves in layers. So we can say that viscosity different kinds of fluids flow more easily than others. Oil, like that, oil, for example, flows more easily than molasses. So this is because the molasses has a higher viscosity, and which is a measure of resistance to flow. It means that viscosity is the measure of resistance to flow, and inside a pipe or a tube, a very thin layer of fluid are right near the walls of the tube and motionless because they get caught up in the microscopic ridge of the tube. Layers closer to the center move faster and fluid shear, and the middle layer moves the fastest. So this is the basically a graphical representation of the viscosity. Now we will understand how to calculate the viscosity that is given by Newton's. So this is the Newton's law of viscosity. According to Newton, the scientist that drive the formula of Newton's law of viscosity. Basically, according to Newton, he states that shear stress on a fluid element layer is directly proportional to the rate of shear strain. Basically, the constant of proportionality is called the coefficient of viscosity. We have tau is the shear stress, and shear stress is directly proportional to the rate of shear strain, and mu is the coefficient of that is viscosity. So du upon dy is the velocity gradient, and mu is the coefficient of viscosity, and du is the change in velocity, and dy is the fluid thickness, and mu is the coefficient of viscosity, and it is also known as coefficient of dynamic viscosity. So we have to know, and on this topic, based on the Newton's law of viscosity, we have to calculate numericals, and in exams, numericals comes under this topic. Now, next topic is that is kinematic viscosity. This kinematic viscosity is different from the dynamic viscosity because the kinematic viscosity is basically the ratio of the dynamic viscosity to the density of the fluid. So we can define as the ratio between the dynamic viscosity and density of the fluid. We can calculate the kinematic viscosity. In case of kinematic viscosity, the unit of SI unit, in case of SI unit, The meter square per second is the unit of kinematic viscosity, and it is calculated on the basis of density and dynamic viscosity of the fluid. Now we will understand how the viscosity varies with the rise or fall in temperature. So we will learn how to understand this process of variation of viscosity with temperature. Basically, in case of liquid and gases, liquid and gases both are the fluids, and in case of liquid, cohesion and momentum transfer occurs, and in case of gases, transfer of molecular momentum occurs. So we can say that the viscosity decrease at temperature increases in case of liquid, but in case of gases, viscosity increase with increase in pressure, as well as viscosity increase with increase in temperature in case of gases. Now we have to understand how the this temperature variation affects graphically on viscosity. So this is a graph that shows we have taken temperature on x-axis and kinematic viscosity on y-axis. On x-axis we have temperature 0 degree, 50 degree, and 100 degree centigrade. But on y-axis we have kinematic viscosity, and whose that unit is meter square per second. Basically, variation of viscosity with temperature we have to understand graphically in a very simple way. Basically, this is a downward curve. So this indicates that when we increasing the temperature of crude oil, we have taken crude oil in this case. So by increasing the temperature of crude oil, then viscosity is decreasing. Which viscosity? Kinematic viscosity, and that is in meter square per second. This is in decreasing way. But in case of air, as we increase the temperature, then viscosity increases. So due to this, this graph increase in upward manner. So we have understand that in case of liquid, the viscosity decrease with increase in temperature, but in case of gases, viscosity increase with increase in temperature. So this is the basic difference in two cases. Now we have to understand what are the different fluids and how these can be understood, and how to learn what are the basic difference in these types of liquids. Basically, we have to know what is ideal fluid, what is real fluid, Newtonian fluid, non-Newtonian fluid, and ideal plastic fluid. Ideal fluid is that fluid which have no viscosity, no surface tension, no compressibility. But in case of real fluid, it has viscosity, surface tension, and compressibility. But in case of Newtonian fluid, we have Newtonian fluid is that fluid which obeys Newton's law of viscosity, in which shear stress is that relation to the shear strain. So this type of liquid is called as Newtonian fluid. In the graphical representation, we have taken dV upon dy on x-axis, dV upon dy known as velocity gradient, and tau is the shear stress taken on y-axis. dV is the change in velocity, and dy is the fluid thickness. So we have to understand how this type of different types of fluid can be representing on the graphically. So we have seen in the figure that Newtonian fluid is this curve. Here the slope of line, this line is called the dynamic viscosity. But in case of shear thinning, so what is shear thinning? This is the line, this curve shows the shear thinning process. This type of shear thinning, it is defined as the ratio of shear stress to the shear strain decreases as shear strain increases. For example, toothpaste and paints are the example of shear thinning. But in case of shear thickening, the graph is known as this is the downward graph. And in this case, the most lower one graph is the shear thickening graph. This graph indicates that viscosity increases with shear rate. For example, glass particle in water and gypsum water mixture shows shear thickening process. So we have to understand this type of process well. Now, what are the various applications of viscosity? So we have to know various applications. So there are 5 to 6 applications are there. That are most important in engineering applications. Basically, first of all is the transparent and storing facility for fluids, that is pipes and tanks. And second one is bitumen used for road construction. Third is the designing of sewer line or any other pipe. Flow viscosity play an important role in finding out its flow behavior. in case of drilling for oil and gas requires sensitive viscosity. But to understand the performance of the machines and automobile by determining the thickness of lubricating oil or motor oil. So these are the various applications of viscosity. Now, what is surface tension? So we will understand the next fluid property that is known as surface tension. Surface tension is the basic concept and it is defined as the ratio of force per unit length. Basically, in the figure, what happening here, the bug is walking on the water surface because of surface tension effect. Surface tension is a contactive tendency of the surface of the fluid that allow it to resist an external force. And the surface tension is an important property that markedly influence the ecosystem. Now we will understand the basic concept of surface tension. So we have in case of surface tension, we have a graph in which we have different molecules. Say molecule in the interior of the liquid. This molecule is in interior of the liquid. A molecule is in the interior of the liquid under attractive force in all the directions. However, a molecule at the surface of the liquid is acting on by a net inward cohesive force that is perpendicular to the surface. Hence, it is required to work to move molecules to the surface against this opposing force, and surface molecule have more energy than interior ones. So we can say that higher force of attraction on the surface. This is the surface. So higher force of attraction on the surface, and it creates a stressed membrane effect. So this is the basic logic regarding the surface tension. If we have to find out the surface tension mathematically, so we can understand the basic concept. Basically, sigma S. Sigma S is the that is shear that is surface tension, and we have to know what is Fs. Fs is called shear surface tension force, and L is the length over which the surface tension occurs. The length is taken in meter, and the unit of surface tension force that is unit is Newton per meter. That is in case of surface tension force, the unit is Newton. But in case of surface tension, the unit is Newton per meter, because surface tension is nothing but only the force per unit length. So the unit of force is Newton and the unit of length is meter. So a whole unit, the unit of surface tension is Newton per meter. So this is the basic formulation of the surface tension. Now we have to find the various examples, or we have to solve the numericals based on the surface tension. So in this case, estimate the difference in pressure in Pascal. P indicate for Pascal, and between the inside and outside of a bubble of air in 20 degree centigrade water. The air bubble is 0.3 mm in diameter. So radius of the air bubble is 0.15 in 10 to 3 meter, and sigma, that is surface tension, is given as 0.073 Newton per meter. We have to find out the difference in pressure. So first one is we have to find out the pressure. Formula for calculating the pressure is 2 sigma upon R. Sigma is the surface tension, whose value is 0.073, but R radius of the air bubble, that is of 0.15 into 10 to 3 meter. So we have to put the values of sigma and R, surface tension and radius of the air bubble. Then it comes that is pressure equal to 970 Pascal. But in case of fluid statics is concerned, the formula is P equal to gamma H, gamma equal to rho g, and gamma is the specific weight. So we have to find out H here. So H equal to P by gamma. So gamma is 9806 and pressure is 974 Pascal. So we have to calculate here 0.1 meter of water is the value of H. So this is the surface tension methods of calculating the internal pressure of the air bubble. Now we have to understand what are the various applications of surface tension in real life. So we have to understand the process. So in this case, we have a different scenario of that is we have seen a figure in the figure, water strider can walk on the water. So this water strider can walk on the water due to the surface tension effect. We have seen that some tents are made impermeable of the rain, but they are not really impermeable. But if water is placed on it, then the water doesn't pass through the fine small pores of the tent cover. but as you touch the cover while water is on it, you break surface tension and water passing through. So this is the basic applications of the surface tension. Now we have to understand the capillary effect. So what is capillary and how the effect is taking place, how this effect takes place. So now the capillary action, what is capillary actions? Basically, we have capillary tube. In case of capillary action, the capillary action is the result of adhesion and cohesion. A liquid that adheres to the material that makes up a tube will be drawn inside, and cohesive force between the molecule of the liquid will connect the molecules that aren't in the direct contact with the inside of the tube. In this way, liquid can crawl up a tube in a pseudo weightless environment, like in the space shuttles, and weightless fluid could crawl right out of the container. So we can say that we have to understand the process of capillary rise and capillary fall, and so we will understand this graphically. So we have capillary action. What is capillary action? Capillary action is the ability of a fluid to flow in a narrow, small space without the assistance of and in opposition to external force, gravity, like the gravity. So we have two figures here. In the first case, we have a vessel in which we have inserted a glass tube that is called the capillary tube, which is of a small diameter. So, and you can see that when we dip this capillary tube in the water, and we have seen that there is a rise of water of height h. Sigma is basically the surface tension here, and theta is the wetting angle. A downward, that is, we have seen the atmospheric pressure. Atmospheric pressure is existing on the surface. In the second case, we have mercury in the container, and we have inserted a glass tube that is called capillary tube in water. So we have seen that a capillary fall of height h going on here, and this is the diameter of the capillary tube, and this arrow indicates the atmospheric pressure that is exerted on the surface. Now we have to understand the basic criteria, that is the difference between the adhesion and cohesion. Basically, adhesion is the force of attraction between the dissimilar molecules, but cohesion is the force of attraction between the similar molecules. Basically, the force of attraction between unlike charges in the atoms, molecules of the substance are responsible for the cohesion and adhesion. So we can say that cohesion is the clinging together of the molecules or the atoms within a substance. Ever wonder why rain falls in drops rather than individual water molecules? It's because water molecules cling together to form drops, and adhesion is the clinging together of molecules or the atoms of the two different substances. Adhesion tape gets its name from the adhesion between the tape and other objects. So water molecules cling to many other materials beside cling to themselves. Now we will have to understand the capillary effect, how the capillary effect takes place, and basically we have to understand the basic parameters of the capillary actions. So we have H. H is denotes the height of capillary rise, or sometimes it denotes the depression. And sigma is the surface tension here, theta is the wetting angle, and G is the specific weight. And we have seen that R is the radius of the tube. So we can see that if the tube is clean, capillary tube is clean, then theta is 0 for the water. We have a formula for calculating the capillary rise or fall. This is 2 sigma cos theta upon gamma r, where gamma is the specific weight and r is the radius of the fluid elements, and r is the radius of the capillary tube here, and sigma is the surface tension, and h is the capillary rise or fall in this case. Basically, the capillary effect can be understood, or capillary rise and falls can be calculated on the basis of this formula, h equal to 2 sigma upon 2 sigma cos theta upon gamma r. Now, come to the next, basically, next is what are the various applications of the capillary actions. So there are different applications of capillary actions which we have to know. We have seen that applications capillary tube. We have seen that capillary action is found in thermometer, where fluid used in it automatically rises when comes in contact with a higher temperature or falls down with lower ones. So capillary action can be performed to transfer fluid from one vessel to another vessel. So this is the various applications of capillary action. Now next is next fluid property is called as vapor pressure. So how what is vapor pressure and how it can be understood? So we have a graph here. On x-axis we have taken temperature in degree centigrade, but on y-axis we have taken absolute pressure in mm of Hg. So we have to understand the effect of temperature on vapor pressure. Basically, vapor pressure, the pressure at which a liquid will boil. This is called vapor pressure. The pressure at which liquid can boil is called the vapor pressure here. And vapor pressure increases with increasing temperature, as we see in the graph. By increasing the temperature from 0 to 120 degrees, we have seen that there is an increase in absolute pressure. So now at atmospheric pressure, water at 100 degrees centigrade will boil, and water can boil at lower temperature if the pressure is lower. So we can say that when vapor pressure is greater than the liquid actual pressure, then it will boil. Now come to the next, that is next fluid properties, that is cavitation. So we have understand in this lecture that there are a number of fluid properties. We have understand what is the mass density, specific gravity, and what is viscosity, what is kinematic viscosity, and vapor pressure. So we have understand different the fluid properties. So last fluid properties that we discussed, and that is very beneficial to the students of Btech mechanical engineering as well as civil engineering for the second year, that is third semester student of comes under AKTU. That is cavitation. What is cavitation? It is the phenomenon of formation of vapor bubble of a flowing liquid in a region where the pressure of the liquid falls below the vapor pressure, and sudden collapsing of these vapor pressure in a region of higher pressure. So in the figure we have seen the cavitation effect. This is basically a plane, and in which the due to cavitations and air bubble, the cavities are formed in this case. And so we have seen that in case of fluid properties are concerned, we have discussed one by one all the fluid properties and understand the concept of all the fluid properties. So in the in the next lectures we have discussed, we have to discuss the numerical problems in deep and how they can be solved. So for that, all students have to prepare the basic, that is the formula and the basic definitions of the fluid properties, on the basis of which they can calculate all the numerical problem. They can calculate all the numeric problems, and whose basic concept first to be cleared. So this is the cavitation. So thank you, student. This is the lecture that is very beneficial to the student of Btech mechanical engineering as well as civil engineering, and the syllabus is AKTU based. AKTU means Abdul Kalam Technical University, Lucknow. So this is the first unit lecture, and this is the first lecture based on the unit number 1 of fluid mechanics. So thank you all for the lecture, and we will meet in the next lecture based on the numerical. Okay, thank you.